Sequences and series. A sequence has a domain that consists of consecutive integers. Okay? The terms of the sequence, that's the items that they list out, that's part of the range. That is the range. Okay? For example, your domain in a sequence is going to be 1, 2, 3, 4, 5, and so on up to n. Your range will be the term that goes with 1, the term that goes with 2, so on and so forth. We have types of sequences. They have finite, that just means they stop, or infinite, which means they continue. And the thing that tells you it continues is the dot, dot, dot. Okay? Both of these are defined by a rule. Okay? It's a function rule. Okay? F of n, where n is the term number, so you want to relate the term number to the term itself. So this function, these two are defined by 2 times n. Okay, if you're asked to describe, we can describe it any way you want. You can say, okay, it's increasing by 2 each time. That's one way to describe it. When you're asked to write the rule, that's where you got to kind of think outside of the box sometimes and forget about, yes, we've got addition and subtraction, but then we also got to remember, oh yeah, multiplication and division, we've got squaring, we've got square rooting, we've got all kinds of things we can use. So, example 1 in your textbook, I decided not to do this, so you can look it over. It's really simple and basic. You can look at that in your book and figure it out. Example 2 talks about writing the rules for different sequences. Okay, so we're going to write the rule for the nth term. That means, okay, n is our term number. What is the nth term? What's the function rule? Okay, what you got to remember is okay, I've got term 1, term 2, term 3, term 4. How do I relate 1 to -1? How do I relate 2 to -8, 3 to -27, so on and so forth? Sometimes you don't see the function rule on the first one. Sometimes you can see it when you compare the first and the second and then the third. You got to look for the pattern. Okay, most people like sequences because you're looking for a pattern. Okay, 1 times -1 is -1. Okay, but 2 times -2 is not -8. But 2 times 2 is 8. And that times -1 is -8, or -2 times -2 times -2, oh, that's -8. How about -3 times -3 times -3? That's -27. So it's safe to say that this is -1 cubed, right? Because -1 cubed is -1. 8 is -2 cubed. I'm relating the term number to the term itself. And the third term is -3 cubed. The fourth term is -4 cubed. So the function rule for this case is -n cubed. That's the nth term. The next one is not, I think that one's more obvious. This one's not so obvious, but it's kind of along those lines. If you think about this, term 1, term 2, term 3, term 4. We've got, what do I do to 1 to get 0? Well, you could subtract 1. Okay. Am I subtracting 1 when I get 2 to 2? No. Alright, how about 1 to get 0? 1 times 0 is 0. That works. What about 2? No, that doesn't work either. But if I think about it in those terms, I've got 1 times 0. Oh. So 2 times what is 2? Oh. 2 times 1. 3 times what is 6? Oh. 3 times 2. You see in the pattern now? And then 4 times 3. So the next one would be what? Oh. 5 times 4. Could have been done the other way, whatever. Alright, so what do I have in terms of n if n is the term number? Well, there's n, there's n, there's n, there's n. What do I do to 1 to get 0? Oh, n minus 1. 2 minus 1, 3 minus 1, 4 minus... There it is. We've got n times n minus 1. Okay? Series and summation notation. A series is the sum of the terms in a sequence. The expression is called the series. That's why sequences and series go together, because they are so very closely related. We have finite series. We have infinite series. Okay? Now, summation notation uses the Greek letter sigma. It's a capital sigma. And it's just another way of stating this. We've got 2 plus 4 plus 6 plus 8. This little statement says all of this. This means, okay, when I read this, I see, oh, I want the sum of the sequence defined by 2 times I, where I is 1 is my first term, and then I'm going to stop when I get to the 4th term in the sequence. Okay? So I want the sum of the sequence defined by 2 times I, where my first term in the series or sequence is going to be 1, and the last one is going to be the 4th one. That's what that says to me. This one down here says the same thing. I want the sum of the sequence defined by 2i, only this time I'm starting at 1 and I'm going on to infinity. Okay, so you have sum of a finite series, and we have a little sigma notation for an infinite series. Summation notation, sigma notation, I'm going to use probably those interchangeably. Okay, writing using summation notation, the first thing you have to do is you have to find the function rule. And the variable you use, it doesn't have to be I like it was in those last two. It doesn't have to be n. You can use x or k or b or z or whatever you want to use. Okay? First of all, let's look at this. We've got 1, 2, 3, and 1 to 5, 2 to 10, 3 to 15. Hopefully you see it. But 5 times n. I'm going to use n since we're used to the nth term. Now to write it in sigma notation, my sigmas are generally atrocious, so just deal with it. So it's going to be the sum of 5n, where n equals 1 is my first term. Now where am I stopping? This one is finite. I'm stopping at, well, 20, or 100 divided by 5 is 20. Okay? This one's a little more challenging. Okay, most people look at this and say, ew, fractions, I'm not going to do it. Don't be that person. Okay, remember, you're just relating the 1 to this, the 2 to this, the 3 to that. Now, I find it easier, especially with fractions, is to deal with the numerators and the denominators separately, because sometimes you have to. If I'm looking here, I see, oh, look, 1, 1, 2, 4, 3, 9, 4, 16. You see that. That's going to be n squared. Okay? So it's 1 squared, 2 squared, 3 squared, 4 squared. Now, 1 plus 1 is 2. 4 plus 1 is 5. You see it? Plus 1, plus 1. So the denominator is going to be n squared plus 1. Okay? There's your function rule. Okay, use your sigma notation, and you're going to use sigma notation or summation notation a lot. Okay, n equals 1, and we're going to infinity this time because it is infinite. And we've got n squared over n squared plus 1. Okay, you're going to see this a lot in pre-calculus and calculus and all that stuff. Because that's how they represent limits. Alright. Look at the key concept box on page 681 in your textbook. That's where this formula comes from. They give you 3 different formulas in that box, but it's your responsibility to find those, get those in your notes, whatever. Okay, example 6 is to find the sum. Here we wrote the sum in summation notation. Now we're actually going to use a formula to find it, and then we're just going to write it out to find this one. Okay? For an I squared, or anything that's a square function, for the sum, the formula is like this. Okay, where n is going to be the last term in the series. Okay, so what we're going to do to find this sum from 1 to 7, we're just going to plug in a 7 right here. So it's 7 times 7 plus 1 times 2 plus 7 plus 1, blah, 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 divided by 6. Do the math. The sum of that is 140. This problem actually comes from a problem in your textbook about a grocery stacking of apples, and it's got a square base, and they've got 7 layers, and they want to know how many apples are in the case. This one doesn't have a special formula that we can use. We just have to actually find all the terms and add them up. But I want to point out here that we're using K instead of N or I, and we're starting at term number 4. We're not starting at term number 1. So this just means 3 plus 4 squared, because we're starting there, plus 3 plus 5 squared, plus 3 plus 6 squared, and so on and so forth. The sum, I believe, is 205. Okay, you can do that on your own. It's just crunching numbers. The assignment was page 682, 3, 7, 11, and then 15 through 55 odd.